So what are you guys?
We're the Smartwood family.
Hi guys, so we want to do a solution for one of the old APs. In fact, we had a request to do in particular AP 2023. All right, 2024 is about to come out anyway, but I guess the more problems, the better. So this is problem number 1 on the free response. Okay. Let me describe briefly what the setup's going to be like. So you have basically a spring. It's got its happy point, equilibrium. It's been stretched out. There's a cart on wheels. Apparently there's no friction, and it's been stretched some amount. So let's say from here to here. I think they'll call this coordinate x equal to plus L. This x equal to 0. And then, over here somewhere, the equivalent. Sorry, it's supposed to be symmetric. Not quite, but it's supposed to be the same left and right. Okay? X equal to negative L. Okay? They also give you a graph. They kind of set this up where they have potential energy over here, kinetic energy over here. So when it's at equilibrium, it does nothing, right? Totally happy. So when you stretch the spring, right, it wants to come back to equilibrium. So it's going to have a force pulling it this way. Likewise, as this guy moves to equilibrium, it'll be moving, so it keeps going, and now the spring is pushing back this way, all the way until it stops, okay? So in this end, you're compressing the spring, and it's pushing back this way, okay? Quick review of springs, just so we're all on the same page. Remember that when you've stretched out here, the moment I let you go, you're not moving at all, so the kinetic energy is 0, okay? And you're all potential energy. So I'll put all pot, okay? So the second you're over here, the spring is happy, right? When the cart's moved over here, it's not stretched, it's not compressed, the spring is happy. So literally it wants to do nothing. So by virtue of your position, nothing is going on. So the potential energy here is going to be 0, which means all you have now is kinetic energy. Okay, so I'm going to say all kinetic. What about the third case over here? When you're fully compressed, again, you've come to a standstill. So the kinetic energy here is 0, right? But now, because you're so compressed, all your energy is invested in your position. The spring is uncomfortable, it's going to push back. So on the left-hand side, you are all potential again. Okay. All right, so that's just a quick review of what's happening with the spring. All right, so let me clean this up, so it's a little easier to understand. So now, if you're looking at the problem actually says, why are the x-intercept and the y-intercept the same? Can you explain it in terms of a physics concept? And in fact, we kind of already have, because that's how we were doing this. So the claim is, if there's no friction or no work being done from the outside, energy is conserved, right? It's the one thing you could depend on. So the theme here is actually conservation of energy. In this case, conservation of mechanical energy. All right, so now I'm going to write across the top, and we're going to get exactly what we need. So let's do this. So conservation of energy, what you start with, potential plus kinetic. If no one's messing with you, it's the same, right? Potential plus kinetic. So if you're not losing energy to, say, friction, and if no one's doing work from the outside, then what you start with is what you end up with. Okay, so let's pick a place here. So maybe in the beginning, you're all potential. It doesn't really matter which end we pick. I'm going to pick this end. So at maximum stretch, okay, all your energy is potential. So it's going to be all potential. I'm going to plug in that number 4, just so you can see it visually. Potential is 4, right? But we said the kinetic energy is what? 0. Okay. And then what happens when you get to, say, equilibrium? Because here, if you notice that the y-intercept, the potential is 0. So you know the potential is 0 when you get to equilibrium. Because at equilibrium, the spring is happy, so your position gives you nothing. Think potential energy is energy due to position. All right, so now we're here. So it's equivalent being right here. So the potential is 0, right? And now it's just literally 4 plus 0, the number can't change, must be 0 plus 4. So what you've really done is you've converted potential energy to kinetic. So on the AP exam, to keep it clean, you want to say something like, by the conservation of energy, right, the energy can't change because there's no work being done from the outside. So by the conservation of energy, the total, I'm going to abbreviate because I don't have room, mechanical energy. So this is mechanical energy, right? You know, I'll write energy. Must be constant. Okay? And that's really going to give it to us. So let's say the total energy. So let's say total energy is equal to, let's call it E. Okay? If that's the case, at the x-intercept, right, what's happening? Well, the x-intercept, if you read, potential, it's potential plus kinetic. So this potential here is 4, right? And the kinetic, just reading this graph, the kinetic energy is the height, and it's 0. So it must be 0, right? And then at the y-intercept, you have, again, potential plus kinetic. So the potential energy, again, just look at the graph. On the y-intercept, the potential energy is 0, and the kinetic must be 4, right? And this is because both of these values give you that total energy, okay? So remember, I wrote this out trying to explain everything. On the AP exam, you can keep this much cleaner. You can say by the conservation of energy, right? The total energy can't change. So on the x-intercept, the total energy, which is 4, is represented purely as potential, as given by the graph. And on the y-intercept, all the energy is given as the kinetic energy, right? Because the potential is set to be 0, okay? But regardless, the total energy involved, which is 4, can't change, okay? In fact, anywhere along this line, the sum of the kinetic plus potential, and again, kinetic plus potential, it's got to be the same. It's always got to be 4. Okay? All right, not too bad. Let's move on to part B.